Buenos días. No voy a intentar hacer esta charla en castellano porque no creo que el castellano sea suficiente para eso. Voy a hablar en inglés, pero también para las preguntas puede ser en castellano, que no tengo tanta confianza en mi capacidad de castellano. So in this talk, I'm going to tell a little bit about my latest project, in which we tried to endeavor a mechanicist analysis of Ross generation on the silver phosphate surface. And although it was talked in extent yesterday, I'm going to talk a little bit about the importance of reactive oxygen species, why we need to be concerned with them. Well, and here are some examples. And Ross, the great thing about Ross is that they are really reactive molecules that can be derived from relatively simple and omnipresent molecules such as oxygen and water. They can be free radicals, or they can be just an excited state away from the ground state, or even according to some definitions, they can be neutral molecules, but with a high oxidative power. And lately, especially because of the COVID pandemics, they have been extensively explored because they can be brought to cause what's called the oxidative stress on living cells. They are naturally produced in the cells, and they are a fundamental part of the cell homeostasis when they are produced, but they are quenched by natural antioxidants. And when you can induce deregulation in favor of ROS production, you can cause what is called oxidative stress and lead to the cell death. When you apply this to fungi, bacterial or viral species, that's the root of their biocidal activity. And when you can target them in specific cells, their overproduction in specific cells, say cancerous cells, they can be used in cancer cell therapy. And also they have some interesting environmental applications given their high reactivity. They are used, for example, in wastewater treatment plants when they are used to oxidize persistent organic pollutants that can't be dealt with conventional means. And they can also be explored because of their biocidal activity. So they are very important and have elicited some interest lately, always, but lately, given the pandemics especially. And semiconductor materials are ideal ways to generate ROS, given their band gap. Their band gap is not so extensive as to demand a great deal of energy to promote electrons from the valence band to the conduction band, so they can be worked in the visible, ultraviolet, and even some cases in the infrared spectrum. And this band gap is ideal to avoid the recombination of the charge, the photoinduced electrons with their holes. And if the alignment of their bands with the reduction potential of the reactions of interest is correct, they can live long enough to partake in these reactions. And as you can see, only they can generate various species of ROS from relatively simple molecules, such as water and oxygen. And in my case, I'm going to talk about the silver phosphate. And why is that? Well, because firstly, it's a crystalline semiconductor with an indirect band gap of suitable length. And being an indirect band gap is ideal to avoid the recombination of charge carriers. And back in 2010, in this seminal work, it was reported that it had high rates for photocatalytic organic dye degradation. And in subsequent studies, including studies by our own center that we associate the CDMF, the Center for Development of Functional Materials. It was also discovered that it had a great activity for fungicide, bactericide, and antiviral activity. And all this hints to its capacity to generate ROS. So that's why we are working with this material. But one added fact is it was also talked in some extent yesterday about the importance of the morphology for the reactivity. And silver phosphate, silver phosphate, these are the main facets that are exposed when they are synthesized. And various experimental protocols have been developed so that you can expose one facet over the others. And that's very good because that's a straightforward way to modulate the electronic properties and thus the catalytic activity by just having different surfaces exposed. And in a prior study, we have explained one well-known experimental fact that crystals that showed a high percentage of 110 and 111 surfaces had a greater photocatalytic activity than crystals that showed only the 100 surface. And we explained in terms of stability, degree of superficial defects, and the recombination ratio for photo-generated electrons and holes, why that is so. And that this is the best surface to generate ROS. And that's why I'm going to talk about silver phosphate and the 110 surface of silver phosphate. And firstly, this is the surface that we have been working with. It has a high degree of defects. This first termination having equally twofold coordinated silver atoms with oxygen atoms, and threefold coordinated with neutral oxygen vacancies. In the book, we only see fourfold coordinated silver atoms. And this first subsurfacial layer has only twofold coordinated. And these defects are important because they create this remarkable trait of the surface that overall it's an electron-poor surface. The oxygen atoms have significantly less electrons than in the book. And even though the silver atoms are slightly less oxidized than in the book, overall, when you sum up everything, still it's an electron-poor surface, the rate of 1 electron per unit cell. This supercell that we worked being comprised of 2 unit cells in the axis contained in the plane. So we are talking about 2 electrons less than it should have had it not had its defects. And first, we analyze the water absorption and decomposition. Water binds very strongly in this surface via this interaction of the surfacial oxygen with the hydrogen. And this interaction causes a significant charge flow from the molecule to the oxygen. Here, this is a charge density isosurface, the red representing charge accumulation and the green charge depletion. And although it may not seem much, we calculated the overall charge transfer in 0.1. We hypothesized that given that the surface is electron poor, the scission of the molecule, the water molecule, would guarantee even greater flow to the surface. And in fact, this is so. After we induce the scission of the molecule, there is an increased flow of 0.45 of charge, 46 of charge to the surface. And given this, the necessity, the tendency of charge flow, we also speculated that because when this bond is broken, the charge flow increases. It wouldn't take much to induce this breaking. And in fact, calculating the reaction path, we see that this breaking involves an activation energy of only 0.14 electrons and results in an overall stabilization of the system. So it's very likely to occur even under normal circumstances. And now, analyzing oxygen adsorption and activation, we see, given that oxygen is a highly electronegative molecule, that the charge flow is the inverse. It's from the surface to the molecule. And the molecule binds considerably less strongly with the surface. And the first question that arose was which species this adsorbed oxygen was becoming. And so we analyzed this adsorbed entity with isolated molecules derived from oxygen and molecules derived from oxygen. These being the singlet oxygen, the superoxide, and the peroxide. And we analyze in terms of bond length, stretching frequency, and this here stands for the integrated projected crystal overlap Hamiltonian population, actually the ratio between alpha electrons and beta electrons, which are indicative of the bonding character contribution of each electron. For instance, for the singlet oxygen, we note that the same number of alpha and beta electrons are in bonding and anti-bonding orbitals. So this contribution of alpha electrons and beta are the same. So it's 1. Now, for triplet oxygen, we note that there is 2 alpha electrons in anti-bonding orbitals. So the contribution of alpha electrons is less than beta electrons. So it's less than 1. And here are the values for isolated superoxide and peroxide. And here are the values for the adsorbed entity. If you compare, you see that it's closer to the superoxide than any other species. We didn't expect to be the exact same value because it's not isolated, it's interacting. So it's safe to say that it assumes a superoxide form. And it's well known in the literature, all the pathways that involve the activation of oxygen until its scission that can even lead to the oxygen radical 2. And one important trait in this chain is that what is called the sufficient excess electron. I think it can be called a theory, because oxygen needs to be activated to interact with a catalyst or a molecule, being a molecule or a surface that is capable of giving enough electrons to go down all the way to this chain. And if, as I said earlier, our surface is electron poor. It doesn't even have excess electrons, much less sufficient excess electrons. So at the first moment, it is only activated in the first step of this chain. And there's nothing wrong about it per se, because it is a ROS, but as ROS goes, it's not very efficient. It would be preferable to receive H plus and become a peroxyl radical, or even better, to go down this chain all the way until its total dissociation. And knowing that, we induced the breaking of the bond to see where this would lead us. And in fact, given the lack of electrons that the surface can provide, this final structure is more unstable, not by much, but more unstable than before the dissociation. But I ask of you to mark that this dissociation causes a great deal of distortion of the surface, a distortion that would demand a significant amount of energy. So it's not likely to occur under these conditions. So the surface is very good to activate water, but not so good to activate oxygen, at least only in this first form. But we see that both species can act like polar opposites, with one withdrawing electronic density and another giving. So we thought to couple the absorption of the two in the surface. And indeed, what we see here, it's the water given density and the oxygen taken. And when they are merely adsorbed, they behave as they have behaved when isolated. But when we induce the breaking of the water bond, we see that this flow is even more pronunciated than before. And the importance of this is because this also this not only provides more charge for the oxygen than before, but it also acts in a way to restore the surface, because in either case, when the molecules are isolated, we see that the surface becomes either positively charged or negatively charged. And in this way, there's a considerable balance between these two. And we also hypothesize that this would benefit both activations. And indeed, when we calculated the reaction path for the dissociation of the water, we see a considerably reduction of the activation potential for less than half, and even more pronunciated stabilization of the final system. And what is interesting is analyzing this entity, the oxygen, after the dissociation. We were faced with the same question for which species it had become. And comparing, we see that there is a considerable stretching of the bond and even more charge being taken up by the beta electrons in the anti-bonding orbital. Not so much as to say that it is a peroxide species, but it is even more so going in that direction. So the last step that we analyzed was how much further to the oxygen bond scission. And so we again induced this breaking and saw that still it was a less stable configuration, even more so than before. But I would like to remember that given that the scission considerably contributes to the stabilization of this final state, even though for the breaking of the oxygen, it would demand a significantly large activation barrier. Given this initial stabilization, this barrier might not be so unfeasible. It might still be more stable than the initial state. And that's a great improvement, we think. But still, the surface doesn't have enough sufficient electrons to guarantee that it would be a more stable state. And to drive home even further the importance of excess electrons in the surface and the role of the breaking of the water bond in this coupled reaction, we induced the breaking of the oxygen molecules, but did not allow the breaking of water. And you can see here very clearly that the final state is even more unstable, even more unlikely to occur without the electrons provided by the breaking of the water. So to sum up everything, the 110 silver phosphate surface, being very electron poor, contributes to the activation of both water and oxygen, but they activate water more effectively than oxygen because of the lack of electrons. That lack of electrons that benefited water activation, but not so much benefit the oxygen activation. And it's only able to activate in the first step of the chain the oxygen, but it's very efficient to activation of the water with a very neglectable barrier. When we couple water and oxygen, the water actuating as the source of electrons and oxygen actuating as the sink, that both reactions contribute to the recuperation of the catalyst, which is a fundamental thing to have in a catalytic system. The activation is still unbalanced, but it's better for both of them. The water, it's even easily activated, and the oxygen is a bit more activated, a little bit more down this chain. We can say that it's somewhere between these two states, or even in this state, if we consider that it's an adsorbed surface, an adsorbed entity. And for future perspectives, we will analyze, we will try to modify the surface to attain the sufficient electron condition, excess electron conditions, giving enough electrons to the surface to facilitate the activation of both water and oxygen, so we can have the best of both worlds. And one easy way to do that is by electron beam radiation, a technique that has been developed and perfected in our group by it started with Professor Juan and Professor Elson in the CDMF. And other lines of inquiry could be working also with the 111 surface to see how it stands as an electronic environment, and even doping as an alternative method to induce these excess electrons. And that's it. I would like to thank both universities that I am part of, the Unicamp Materials Lab, Simulations Lab, whose head is Professor Miguel, who has, since my master, helped me a lot with my research. The CDMF, who also has the main body of experimentalists, from which all these results started, and these Brazilian agencies for financing all the research. And thank you.
Thanks, Felipe. Nice presentation. There's a point I think I have missed related with the role of light. I mean, at the beginning of your presentation, you speak a bit about your material, the silver phosphate, and you said about the exciting electron from the valence band to the conduction band in order to reduce the molecules, something like that. But finally, the light is not involved in the studies you have done.
Yes, we didn't deal with the role of light just as the silver phosphate, as merely as a catalyst. One future line of inquiry too, we would like to pursue the role of holes and excited electrons in the system. We would like to, with the functional and also introducing some electronegative species in the other end to induce the formation of holes. We would like to explore more of this, but we didn't deal directly with the role of light, and which, given the semiconductor nature of the material, I think would improve greatly the activation barriers and the activation.
Because the processes you have studied or experimentally, they haven't been studied, are in the presence of light. I mean, the material is absorbing light and then promoting electrons to the conduction band, and then electrons can go to the surface and then enrich the surface to interact with the water or oxygen.
Yes, the experimental results have been all in the presence of the light. And in part, let me show here a moment. Okay. They have been, this you are talking about the role of light exciting these electrons. And we have only dealt, just a moment, here in this study, we have considered the effect of the whole crystal, because one of the things that we studied was when all of the surface would be in contact by the work function. And when this is so, one of the effects that we didn't deal is that the electrons tend to migrate to the surface, given their being electron poor. That also considers this. But in this system, one of the limitations that we have is we have to deal only with the one zero surface isolated and alone. So we cannot see this naturally induced electron flow. And one way of considering this in introduction the role of light would be to have other surfaces and, or as I say, to induce the formation of holes and by adding electronegative species in this termination. But we didn't do that. Just to see that it's a great material, it's a great catalyst, even without the light. And with the light, it should be even better.
Okay, thanks.
Thank you, Felipe. I have a question regarding what you mentioned about the surface that is might move or reconstruct somehow. So have you considered these effects? Because your species, when they are stabilized, they can be, yeah, if everything is moving around, they might be further stabilized or even destabilized. So did you consider at some point, or do you think it's an important phenomenon that could happen?
Yes, one other line of inquiry that we are dealing with is that this surface was obtained merely by an electronic a relaxation at 0 Kelvin. One effect to consider this capacity to the surface to move about was to apply molecular dynamic to through time to see how the surface is behaving in terms of energy and configuration and analyze several points in time of the simulation to see how it works how it affects the process as a whole. But yes, you're right. And one of the traits of this surface that I have seen that's different from others that I have read similar research than mine is that it moves around a lot when it interacts with molecules, especially when the oxygen is broken. In some other surfaces, this not tend to occur with this degree. So this should affect greatly the catalytic potential. So we are going to do that with a molecular dynamic simulation and analyze different points of this simulation.